want to start off with this problem, which is a nice classic problem, a vintage problem. Set the Wayback Machine to Calc 1 for this kind of problem. We've got a function, and we want to find the critical points, and we want to classify each critical point as a local minimum, a local maximum, or neither of those. So the process is nice and straightforward. We know what to do here because it's the Calc 1 survival skill. Take the derivative when you're handed a function in Calc 1, you take the derivative, set it equal to 0, and solve, and then just kind of figure out what. Then you go back and read the question and see what you wanted to know. So find the critical points of f. This is where we solve f prime of x equals 0. Take the derivative, set it equal to 0, and then solve. When it comes to classifying each critical point as a local maximum, a local minimum, or neither of those, we have a few options. We've got a zero derivative option where we think about what the function looks like. So in this case, to classify, we can use the function. If we know stuff about what the function looks like, then we can use that information. We could use the first derivative. We can note where the function is changing direction. The first derivative tells us about the direction of the function. We can note where the derivative is changing direction. And our other option is to use the second derivative to check the concavity. So we have lots of tools at our disposal depending on how we want to proceed. But the process is familiar. Take the first derivative, set it equal to 0, and solve. And then classify. In the classify category, we could either use what we know about the function, use the first derivative to find out where it's changing direction, or use the concavity to conclude that we're changing direction. All right. So to do this problem, we're going to need the first derivative. So f prime of x will be 3x squared minus 6x minus 9. We're going to set that equal to 0 and then solve. Because I'm so lazy, I picked something that was easily factorable. So we can factor out the 3. That leaves x squared minus 2x minus 3. And the x squared factors out. The quadratic part factors out. So we get x plus 1 and an x minus 3 equals 0. So there's our first derivative. We set it equal to 0 and solve. And we find our two critical points are at -1 and 3. So we got two critical points. I know originally I said find the critical points, and here I found the locations of the critical points, and that would, to find out the actual points, I would have to plug these into the function, and that just sounds like a lot of work, especially if we're going to be looking at a graph in a minute anyway. Now we want to classify each one as a local maximum, a local minimum, or neither. Now, if we want to use the function to do this, we could, this is going to be very simple because we know a lot about polynomial functions. We've got an odd degree polynomial with a positive leading coefficient. So in the classify category, if we're going to use the function, we know that f is odd degree polynomial with positive leading coefficients. More than just an odd degree polynomial, we know that it's a third degree polynomial, so it makes a maximum of 2 changes in direction. So more than just odd, it's a third degree polynomial. And we know that a third degree polynomial makes a maximum of 2 changes in direction. So our third degree polynomial with a positive leading coefficient makes a maximum of 2 changes in direction. Since we have 2 critical points, these are probably our 2 changes in direction. So this is our most likely shape of the graph. We know that it has to do this because we have a positive leading coefficient. So as x goes to infinity, our function goes to infinity. So the first thing that we use is the fact that there's a positive leading coefficient. So as x goes to infinity, our function will be going to infinity. Since there is an odd degree, the ends have to be going in opposite directions. So I know it's going down this way because it's an odd degree. So second, I look at here and it's an odd degree. And it makes a maximum of 2 or 0 turns. So there can be a maximum of 2 or 0 changes in direction. Since there are 2 critical points, the most likely thing is that we are dealing with 2 changes in direction. So now we're going to use the fact that there are 2 critical points. So the third thing I look at is that there's 2 critical points. So based on this information, based on what we know about the graph, because I picked the easiest possible example that I could think of, we can decide based on the function itself that we have a local maximum at -1 and a local minimum at 3. So we have found the critical points, and then we use the function itself to classify those critical points. But we have options. We have the first derivative sitting right there in our hands. We could use the first derivative. We could decide where the function is changing direction. We can use the first derivative to decide where the function is changing direction. So if I think of a number line, these 2 critical points at -1 and +3, divide the number line up into these 3 intervals. Before -1, between -1 and 3, and then after 3. So I can use the first derivative to determine the direction on each of those intervals. So f prime is 0 at 3 and at -1. And now I'm just going to look at in between in the intervals. All we need to do is pick a value in each of these intervals and then plug it into the first derivative. So I'm going to pick my favorites, 0. And I'm going to say find out what f prime of 0 is. F prime of 0 is going to be -9. So most importantly, on the interval from -1 to 3, f prime is negative. So f is decreasing. So now we know what's going on in the middle. If we see that the function is increasing before -1, then we know we've got a maximum at -1. So let's test something. Let's pick something that's less than -1. -2 would be kind of a pain in the butt to plug in, so I'm going to pick something a little easier to plug in. Make your life easy whenever possible. It's the whole point of life, is to make things as easy as possible. And there's where I want to plug in 10, because that gives me a 300 right off the bat, -60 -9. It's easy to plug in because polynomials are just numbers. Let's switch from the base x to the most common base that we use, 10. So we see that the first derivative in before -1 is negative. So I'm sorry, positive. So we see that the function is increasing before -1. So at -1, we are changing from increasing to decreasing. That means we're at a local maximum. And then we just repeat this process for our third interval. Once again, oops, -10. I was going to do this one next, and I switched to this one. Still at 300 because it's squared. The 60 is going to be positive. I'll edit that later so it looks like I didn't mess that up. I'm just kidding. I don't edit my videos. So here we are using the first derivative, just the first derivative, looking at the direction on each of the intervals. At -1 and 3, the critical points, that's where the first derivative is 0. That's the only place that it has a chance to be changing direction. That's the only place we have a chance for a local maximum or a local minimum. But this leads us to the same conclusion. Therefore, there's a local maximum at -1 because we changed from increasing to decreasing. And there's a local minimum at x equals 3 because we're changing from decreasing to increasing. These two, of course, are not our only options. We also have the second derivative. We know about the second derivative, so we can use that to classify our critical points. Our second derivative is going to be 6x minus 6. We'll just check the critical points check the critical points in the second derivative to determine whether the function is concave up or concave down. So I'm going to do f double prime of -1. -6 minus 6 is -12, and that is less than 0. So when the second derivative is negative, that means the function is concave down. And that means we have a local max. Then we do the same thing for our other critical points. We just check the second derivative at that critical point. F double prime at 3 is 6 times 3 minus 6, or positive 12, which is positive. So at positive 3, F is concave up. So therefore, we're dealing with the local minimum. This last method is a little bit risky because if our second derivative is 0, then we don't know. We don't get information. So there's a little bit of a risk with this last one. It's not that we don't know. That's a bad way to phrase it. Then the second derivative test is not telling us anything. We do not get any information from the second derivative test. This does not mean we say that this is inconclusive. We have to classify the points as maximum, minimum, or neither. We have to do something. We don't just get to say, oh, I don't know. It's the second derivative test tells us nothing. That means do something else because there is an answer. It has to be one of those 3 options. It's just that the second derivative test is giving us the Willy Wonka. You get nothing. Good day, sir. Any questions? So, what are we going to do with this little reminder of how things work? What's the only thing we ever do in Calc 3? We take a Calc 1 problem like we have here, and we make it a function of 2 variables. That's all we ever do. That's why this class is so simple. All we have to do now is look at a function of 2 variables. And I'm gonna steal one. I'm gonna steal this one. 8y cubed, 12x minus plus 12x squared minus 24xy. And I'm gonna ask the same questions. Find the critical points of F. I'm going to be abbreviating my questions, so classify new kind of function, the kind that we encountered here in Calc 3. Same question. Find the critical points, classify each critical point. So this raises the question, how do we do this? we do the same thing what we did last time. Take the first derivative, set it equal to 0, and solve. So our instructions on the last problem were to solve f prime of x equals 0. But we have a problem here. It's not a function of one variable. There are two variables, so that means there are two first partial derivatives. So we're going to have to modify this. I have two partial derivatives, fx at xy and fy at xy. But the brief in Calc 1, the survival skill in Calc 1 is take the derivative, set it equal to 0, and solve. So that's what we're going to do. Note that in this case, we're getting a system of equations. We're getting two equations with two variables. So we get a system of equations. What are our options for classifying them? Well, let's see if we have the same options. Use what we know about the function. This one might be a little bit tricky because it's difficult, even though this is just a polynomial function, it's some weird surface in R3, and it's going to be hard to picture. So that's a little bit tricky. Use f prime. Oh, we don't have f prime. We have to upgrade that. But use our first partial derivatives to think about direction and how things are changing in direction. So we're thinking in this case, we would be thinking about direction. Direction is a little bit weird of a word here because we don't just have the assumed x is going to the right, because I've got the x direction and the y direction. So I got to think about increase and decrease in the x and the y direction. Thinking about increase and decrease still, but now we're thinking in x direction and in the y direction. And then our third option was to use the second derivative. Where we're thinking about concavity. Oh, but now we're in a pickle because there is no second derivative. It's not the second derivative. There are 4 second derivatives. That's from a show that's older than all of you. I don't know how much Star Trek y'all have watched, but I can't say that there are 4 of anything without thinking of Patrick Stewart shouting there are 4 lights. I just finished Picard season 3, so. My new assessment of shows, when someone asks me if something that I watched was good or bad, I don't really commit to one or the other. I just report whether I liked it. And if they ask, I might explain why I liked it, if I happen to know in that case. But the problem is there are things that I definitely like that I can clearly identify are not good. Like if you ask me what the best movie franchise of all time is, the obvious answer is The Fast and the Furious. I mean, there's just no question about it. But is The Fast and the Furious, are any of those good movies? Not really. I mean, they don't make any sense. The characters are all cardboard cutouts. And cardboard cutouts of an archetype that I kind of find in the real world really annoying. Like I would not like these people in real life, but I will watch them go on adventures and root for them the whole time. Anyway, you know what I'm talking about? So I recognize that it's not like highbrow quality entertainment, but yeah. Anyway. What are we talking about? Oh yeah. So we have this problem. In the previous problem, I was able to use the second derivative, just plug stuff into the second derivative to check concavity, but there are 4 second partial derivatives. I know there are really only 3 because those 2 mixed second partials are going to be equal, but there are 4 second partial derivatives. So we're going to have to figure out a way to combine. How do we use all 4? How can we use all 4 of these to check concavity? So that's the question. But we want to see that we have the same options that we had before. We want to see how we can modify those options, the same thing that we did before in this, with this new function. So let's just try to work it out. Let's just do that. We've got a plan. Let's try executing our plan. I need first partial derivatives. Fx at xy is going to be, well, that's constant, 24x to the 1 minus 24y. So 8y cubed is a constant term with respect to x. And in the negative 24xy, that y is a constant factor with respect to x. We've got another partial derivative, first partial derivative, fy. The derivative of 8y cubed is 24y squared. 12x squared is a constant term with respect to y, so the derivative is 0. And the derivative of negative 24xy, the x is a constant factor. The derivative of y is 1, so I'll have minus 24x. So there are 2 first partial derivatives. Our plan is to set these equal to 0 and then solve. And now we're kind of at a new place because we're trying to solve a nonlinear system of equations. We spend a lot of time solving linear systems. This is a nonlinear system. The reason that we spend a lot of time solving linear systems and not solving nonlinear systems is because linear systems, there's a set procedure that we can establish and say, do this to solve a linear system, and it will always work. And everybody's like, oh, yeah, sweet. We got all these different methods. The problem is when we get to nonlinear systems, there's not one thing that we could tell you to do. So the instructions for solving nonlinear systems are essentially do something. And hopefully you have enough understanding of how equations work that you can think of something to do. So let's follow our instructions for solving nonlinear systems and do something. This first equation I like. Does anybody know why do I like that first equation so much? What does it tell us? What's that? It's easy to factor. I can dump 24, right? We're setting equal to 0. We can dump out that 24. What's left over? What is that telling us? X and Y are equal. Perfect. That's what we want to see from that first equation, right? A lot of times we think too much about procedure. So what are these equations telling us? This first equation, we can go through the stuff, but we could take out the 24. 24 is not equal to 0, so that tells us that x minus y must equal 0, if you didn't like my divide by 24 business. And if x minus y equals 0, when we subtract things and come up with 0, that means those things are equal. That's good intel. That tells us whatever critical points we find, they are going to be on this line x equals y. The x coordinate, and if we find a y coordinate, we got an x coordinate as well. Find an x coordinate, we got a y coordinate as well. So that's good. We could also do the main something that we have. Like of all of our techniques for solving linear systems, the most useful one, is substitution. Take this, plug it into the other equation. So now we can substitute. That's why substitution is so much better than like elimination or just like Cramer's rule, but Cramer's rule is fun because it's like weird. If we can solve one of the equations for one of the variables, then we can just substitute that into the other equation. So that makes this second equation look like 24x squared minus 24x equals 0. And this one we like because it drops out 2 x's. Once we have 2 x's, we have 2 y's. So I like that. This one is also factorable. That's why the 8 and the 12 paired with the 3 and the 2 and the 24 sticking out here. So we could drop out the 24. That leaves an x squared. I should have just taken the x out as well. And we can see our two x values. So x equals 0 and x equals 1. So we've got two critical points. If x is 0, then since x equals y, y is 0. And if x is 1, then since x equals y, y is 1. So if x is 0, that means y is 0. And if x is 1, then y is 1. So F has two critical points. Like before, just like in the previous problem, I'm just stating the location of the critical points, not the entire point. I could plug these into the function to find out the whole point, when these are specifically the locations of the critical points. 0, 0, and 1, 1 are not actually points on this surface. They're just locations under the surface. Just like when I said the critical points were -1 and 3, those were X values where we will find the critical points. We didn't actually plug in to find out what those critical points were. Specifically because the problem did not say find the local maximum and local minimum values. It just said classify each critical point as a local maximum or local minimum. It was not in the brief to find out what those actual values, function values were. Questions? And now we have some stuff to think about because this function is some surface in R3, and I don't know what it looks like. So using the function to figure out what's going on with each of these at each of these points is going to be a little bit tricky. Thinking about intervals of increase and decrease, that's also, that might be a little bit tricky because I'd have this plane, there's only these 2 points. How are we going to divide up an entire plane? With the x-axis, with R1, that's easy. 1 point splits the number line in 2 parts. 2 points split the number line into 3 intervals. We just get intervals, very easy to analyze. But I have this 1 point 0, 0. That doesn't divide the plane up in kind of a useful way. There's at that point, and then there's not that point. There's not left side, right side, above, and below. So that's a little bit tricky. Let's see what we get from our second derivatives. There are 4, really 3, but 4 second partial derivatives where we could try to think about concavity. Let's see if that produces anything. So fxx is going to be 24. Fxy is going to be -24. Fyx is also going to be -24. We knew that those were going to be the same, but it's nice to take those derivatives to find out if we're looking at the right function in the first place. So there, that's a little reassuring. I feel reassured now. And then Fyy is going to be 48y. So fxx and fxy are going to be positive and negative everywhere, respectively. Fyy is going to be negative when y is negative, and positive when y is positive, and 0 when y is 0. So at our critical point 0, 0, now what we got to do is think about what the second derivative is telling us and how we're going to interpret that in this scenario. We've got a mixture of positives and negatives and zeros. So we've got this mixture of positives, negatives, and zeros. Second partials Our second partial derivatives are this mix of positive, negatives, and zeros at the critical points. So we got to think about how we're going to interpret this. There are some things that we want to note about interpreting these four, really three, but four four second partial derivatives. The first is to note that we are on page 2 of the notes. And I rarely go past page 2 of the notes. The second thing to note is that we are really close to the bottom of this piece of paper. It's not paper, it's plastic, this piece of plastic. So thing number 2 to note is that I'm pretty much out of space down here for any kind of lengthy explanation. Even though when I write one line, it takes me 20 minutes to read it just because of the way that I am. I'd apologize for that, but I don't think I'm really sorry, and there's no way I could change. So there's not really a point to me being sorry. Do you know what I mean? This is a problem that I'm just not going to be able to fix at this stage of my life. So what we want to conclude from those two things is that this is probably a question that I'm not going to be answering today. And I'm just going to leave it up to you to sort that out. Now, when you show up tomorrow, I'm going to assume that I did explain this and just ask you what the answer is. I'll be like, well, hey, remember when I explained this yesterday? And you'll be like, oh, that's not what happened. You left us on a cliffhanger yesterday. I was like, oh, nah, I would never do that. So I want you to think about, before you look it up, because this is something easy to look up. I could explain, this could have been done like way back up here. I said, just do this, but that sucks. That's shitty storytelling. So I want you to think about how we interpret the second derivative normally and what these things are telling us. This is the other reason I picked this one. It has a nice mix. Some positive second derivative, some negative second derivative, some zero second derivative. What do each of those three kinds of second derivative mean in our normal case, our single variable case? I want to make that normal. I'm trying to normalize this. How will that interpretation apply here? Any questions? The other piece of intel that you have is that I did get this problem. Oops. I did get this problem right from the book, so that way you'd have a good place to go look it up, right? So this is example 4. Figure 15.10 means this is probably in chapter 15. Did we finish chapter 14? It's like, oh no, but Leach is a pain in the ass that way. Sometimes he just decides to go, this is what he wants to talk about. 15.1, example 4. That's the function that you're dealing with. But think about it first. Uh-oh, you've seen it now. Think about what those second derivatives tell you, and then try to combine that with other information like your graph. So you can use the function itself, looking at the graph. Any questions? Comments? Snide remarks? All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.